Welcome. In this module, we will discuss logic synthesis. As mentioned in the introductory lectures, logic synthesis comes after the high-level synthesis step. The objective of high-level synthesis was to obtain a macro-level architecture of the circuit in terms of functional units, number of registers, numbers and types of muxes, demuxes, buses, etc. The objective of the logic design or logic synthesis, on the other hand, is to obtain the micro level architecture of the circuit in terms of gates and flip-flops. So, the input to the logic synthesis step are in terms of the RTL assignments and FSMs. So, at the output of the high level synthesis step, we obtained a set of RTL assignments, register transfer level assignments, and we said that the controller FSM will control at which time step which of these RTL assignments are to be excited or activated. Now this controller FSM and the RTL assignments come as input to the logic synthesis step, and the output to the logic synthesis step is a structural realization of the circuit through gates and flip-flops, and the data structure that is used to represent such a structural realization is called a gate level netlist. So logic synthesis process starts with an FSM specification and culminates in a structural realization in the form of a sequential circuit. As we know, a sequential circuit consists of memory elements along with optional combinational elements as well. This figure shows the overall structure of any sequential circuit. It has an optional combinational part, it has memory elements and outputs. The outputs are also optional. The inputs to the memory elements and the outputs are a function of the outputs of the memory elements, which are fed back to the combinational part, and also the external inputs. The memory elements are realized through flip-flops. However, realizing a sequential circuit design in terms of gates and flip-flops also requires many optimization steps. And why are essentially these optimizations required? Because the gate level design has also many choices in terms of the delay, performance and power requirements of the circuit. Fundamentally, two sequential circuits may exhibit the same I/O behavior but contain a different number of internal states. So therefore, the design must be simplified by reducing the number of gates and flip-flops. Now, basically, reducing the number of states also reduces the cost of the circuit. So what are the basic steps in logic synthesis? The first is state reduction, then state encoding and assignment. Then we have to choose resources, the types of flip-flops and gates to use. Then we have to derive flip-flop input equations and output equations for the type of flip-flop that we have chosen, and we have to do logic minimization. After all these steps, we will obtain a structural realization of the circuit. So the first step, state reduction. So what is the objective? Reduce the number of flip-flops in a sequential circuit while keeping the external I/O requirements unchanged. So we want to reduce the number of states. We said that there can be two different realizations with two different number of states for the same input-output behavior. Since m flip-flops produce 2 to the power m states, a reduction in the number of states may result in a reduction in the number of flip-flops. So we know that each flip-flop can hold one bit of information. Through one flip-flop, I can define two states, and hence to obtain a structural realization of an FSM which has 2 to the power m states, we require at least m flip-flops. However, reduction of states may or may not result in the reduction in the number of flip-flops. For example, let us say if the number of states in an FSM is between 8 and 16, we require at least 4 flip-flops. So if we reduce the number of states from say 15 to 9, we will still require 4 flip-flops. to obtain a structural realization of this FSM, and hence we won't obtain a reduction in the number of flip-flops. However, if we are still using that same 4 flip-flop design, and then we have done a state reduction, and this reduction has resulted in the number of states reducing from 12 to 7, then previously if you were using 4 flip-flops, now we will be able to realize the same design using 3 flip-flops. An unpredictable effect in reducing the number of flip-flops is that sometimes the equivalent circuit may require more combinational gates. And why is that so? Because I have reduced the number of states, we require more combinational logic to obtain the inputs, and hence the resulting circuit may have a bigger area, may require a bigger area than the circuit which used more flip-flops. Now we will understand how state reduction is realized. We will take this sample FSM for understanding how state reduction is done. So in this FSM we see that A is the initial state. This FSM consists of 7 states, A, B, C, D, E, F, G. On this FSM, we will now take a sample sequence and see what is the input-output sequence and what are the next states. So the initial state is A. When we get the input 0, we produce the output 0 and go to the next state A. If the current state is A and the input is 1, we produce the output 0 and go to the next state B. Now, how do we do state reduction? We do state reduction by finding out equivalent states. 2 states are equivalent if for each member of the set of inputs they give exactly the same output and send the circuit either to the same state or an equivalent state. So let us say we have 2 arbitrary states x and y. What do we have to do? We have to find out that for all possible inputs, here we have 2 inputs 0 and 1. Do they go on each of these inputs to the same next state, and do they produce the same output? If that is so, then we can say that these 2 states are equivalent. And if 2 states are equivalent over all sets of inputs, they produce the same next state and same output, then we can remove one of these states. This is how we do state reduction. In this FSM that we have, we obtain the corresponding state table first. Here there are 2 states G and E which are equivalent. And why are they equivalent? Because for both these states, when the input is x equals to 0, they go to the same next state A. When the input is 1, on the other hand, they go to the same next state F. When the input is x, both of them produce the same output. And when the input is x equals to 1, they again produce the same output 1. So in terms of both next states and outputs, they are same. And hence, one of these states here, G, we have decided to remove. So the row with present state G is removed and state G is replaced by state E each time it occurs in the next state columns. So when G is removed, G cannot appear in the next state columns anymore. So wherever G was previously there, if you see the previous state, G, here at F we had G. So we have to replace this G with the E, because for each place in the next state columns where G occurred, we have to now replace it with E. And then we have to continue the same thing. After G is removed and G has been replaced by E in the next state columns, we see that the present state F now has next states E and F and output 0 and 1 for x equals to 0 and x equals to 1. Same next states and outputs for D as well. So what we are trying to point is that D and F are equivalent. Hence, we can remove one of them. Here we have decided to remove F. So if we remove F, then all the places in the next state columns where F is currently there has to be changed with D. So likewise we see that here we have D and here again we have D. So therefore state F can be removed and replaced by D. We finally obtain this realization of the FSM. It is a reduced FSM. The original FSM contains 7 states. The changed FSM now contains 5 states. However, we will see that for all sequences of inputs, it is going to produce the same sequences of outputs, and hence both the input output behavior of both these FSMs are identical. After obtaining such a state reduction, we will now have to do state assignment. Now, a structural realization cannot use the letter names for the states A, B, C, D, E. We have to use binary coded names. And therefore, we have to use an encoding scheme and encode the states with that particular encoding scheme. Here we have shown 3 distinct encoding schemes. So this one is a simple binary encoding, this one is gray code, and this one is one hot encoding. And in this diagram, we have shown that with simple binary encoding, this is what we get. When the input is A, we have represented A with 0, 0, 0, 0, and the present state is x equals to 0. We remain at the same state A, and hence the output state is also 0, 0, 0. Right? The present state is 0, 0, which is A, and the next state will also be A, and hence this is also 0, 0. When the input x equals to 1, it goes to state B and produces output 0. So therefore, B has been encoded with 0, 0, 1, and the output produced is 0. The encoding scheme is this: A is 0, 0, 0, B is 0, 0, 1, C is 0, 1, 0, D is 0, 1, 1, and E is 1, 0, 0. This is the simple encoding scheme that we have used. Okay, and after we have obtained the state encoding, now we have a reduced FSM with binary coded encoding scheme, and now we are ready to obtain a design. The next work is to choose flip-flops, and here we have chosen D flip-flops to design. Okay, we have taken another sample FSM. This is a mood type FSM. The output is produced at the states. Here is an assignment using the simple binary scheme. Because this is a 4-state FSM, it can be realized using 2 flip-flops. And the state encoding that we have chosen is simple binary, and S0 here is 0, 0, S1 is 0, 1, S2 is 1, 0, and S3 is 1, 1. Right, and here is the state table corresponding to the state diagram here, and when the present state AB is 0, 0, that is we are at S0, and the input is 0, we remain at 0, 0, that is in S0, and the output produced again is 0. When the present state is 0, 0, and the input is 1, we produce the next state 0, 1, that is we go to S1, and the output is again 0. At S1, again say at 0, when the present state is 0, 1 at S1, when the input is 0, we go back to state S0, and the output is 0, and likewise we proceed. Now from this state table, we can obtain the flip-flop input equations and the output equations. Now, because this is a D flip-flop, it is simple to obtain, because the next state values in the state table specify the D input conditions for the flip-flop, and hence the next state values tell me the D input conditions. Right? So we want to obtain the input conditions for the D flip-flops and the output. Right? So AT plus 1 equals to DAABX equals to 3, 5, 7. Minterm number 3, minterm number 5 and minterm number 7 produce a 1 here. Right? We see that this one and this one produce a 1. So minterm number 3, 5 and 7 produce a 1. For B, we see that a 1 is produced here, here and here. So at minterm number 1, minterm number 5 and minterm number 7. So the output is produced for 1, 5, 7. And the output YABX equals to 6, 7. Why? Because the output is 1 in these two rows. So this is minterm number 6 and minterm number 7. So after we have obtained the conditions for which the flip-flop inputs and the outputs should be 1, we will try to do a logic minimization. Here we have shown a very simple logic minimization using Karnaugh maps. So next state values in the state table specify the D input conditions for the flip-flop. And we know that because it is 3, 5, 7, this one is 0, 1, 1, 3, this one is 1, 0, 1, which is 5, and this one is 1, 1, 1, which is 7. And after simplification of this, we find that dA equals to AX plus BX. Likewise, we obtain for DB equals to AX plus B bar X and Y equals to AB. So this is how we obtain the input equations and output equation. After obtaining the input equations and output equation, we can obtain a structural realization of the circuit. Here we see that this one produces AX, this one produces BX, this one produces BX, this one is B, and this one is X, and hence this gate produces BX, and this D equals to AX plus BX. Similarly, for this input we see that it is equals to AX plus B bar X and Y equals to AB. We come to the end of this module.